Everybody hanging in there okay? This month of the, like, there's no break, is there? We had Labor Day and we have Thanksgiving, we have like nothing in between. It goes, October is a long month, 31 full days to get through. But we're getting there. Semester, I'm noticing the weather's getting cooler. I drove up to climb a mountain on Sunday. And so of course I drive up there, and what I usually do is I sleep in my car, because you don't want to have to wake up in the morning and drive to the trailhead first thing. You want to already be there. So you just hop out of your car and start walking on your climb. And I just about froze to death. I was parking at like 10,000 feet or something of elevation. I was going to climb this 13,000-foot mountain. It was cold. I think my car was frosting over. It was like 30 degrees or something. I was like, yeah, this is not summertime anymore. So I did that, and I made it up the mountain. I was cold the whole way up on the hike, but I made it back down, and sure enough, it was 85 by the time I could drive back into Orange County. So depends on where you are in the state, what the temperature is going to be doing. Anyway, hopefully you guys had a good weekend as well and are hanging in there with as much as possible with everything you've got going on. I know there's a lot. I have office hours. Don't forget today after class, and also Thursday. For this week, we have an assignment due on Thursday. So hopefully, I know that I didn't really get through all of this recurrence relation material by last week. So I'm imagining some of those homework problems are a little bit fuzzy still. We're going to hopefully get all of that cleared up today, so that'll be something you can work on. But I'll be around later on if you want to stop by and chat about any of that. And then at some point I'll put up I think the next assignment might be up. It's also on chapter 7. We're going to try to get into generating functions probably by Thursday at the latest. So we're right on schedule. Everything is going right up to par so far. Questions? Everybody good so far with all that? Okay, so last Thursday, gosh, it feels like a long time ago. That's what happens when I drive out of town for the weekend. We started talking about using recurrence relations to solve counting problems. And in other words, we can solve sort of the n version of a counting problem, whether it be, I don't know, n bit strings or n tiles or n objects lined up in a row or something. We can solve a counting problem about that by rephrasing that problem in terms of the same problem with less objects or less tiles or less bit strings. And that is done through this device of a recurrence relation. So we gave some examples of this last time, and I mentioned two very important skills. So a good example was the Towers of Hanoi problem, where the objects were just stacked up on a pole and we were taking moves to move the objects around. So the two main skills that we needed to solve that problem was, first of all, we had to set up the recurrence relation in the first place, which actually, from my perspective, is maybe the harder part of this two-step process, because there's a little bit of creativity that has to go into that sometimes. You have to figure out, how do I sort of get this problem straight in my head as to how to break it down as a recurrence relation. And then the second part of it, which there is some homework on this, and of course I haven't covered it yet, so we got to do this today. How do you actually solve the recurrence relations? So that turns out to be just cookbook stuff. Like, it's like, okay, if the recurrence relation looks like this, then you solve it by doing that. And I'll go through all of that today. It's going to remind you potentially of how we solve differential equations. There will be some similar spirit of sort of how you think about that process. So I'll show you what I mean when we get into that. Before I go to step 2, though, I want to practice on step 1 a little bit more, setting up a recurrence relation for a problem. I did a bit strings example kind of at the end of class on Thursday. I know it's a while ago. I thought I'd warm up with you guys today on a slightly harder one, where we're actually going to use ternary strings. These are strings of zeros, ones, and twos. So bit strings would normally just be 0 and 1. Now I'm going to allow twos also. And we want to set up a relation for the number, I'll call it a sub n, of ternary strings that have 3 consecutive zeros in them. That have 3 zeros in a row. So if I want to know how many ternary strings of like 20 have 3 zeros in a row somewhere in that string, that would be a very difficult problem to just solve by any of the means that we've learned up until now. So the idea behind recurrence relations is to express this problem in terms of a smaller and easier version of the same problem. Okay, so let's try this problem. Let's see if we can make some headway on how to solve this one. The idea behind this is actually to describe a sub n as a sum of terms that have no overlap. So that you're not doing, you don't really want to do inclusion exclusion where you have to kind of take a bunch of cases and figure out overlaps and subtract out overlaps and stuff. It's much better if we can kind of organize these ternary strings in this case in such a way that every ternary string that we want to count is listed in the cases exactly one time. No overlap, no multiple counting, anything like that. So what I would recommend is we could write it like this: such ternary strings fall into exactly one case below. All right, so we're going to break down this counting into cases. So the first case, I guess I'll call it case 1, would be if our ternary string actually already started with 3 zeros in a row to begin with. So we have 0, 0, 0 already. These are slots here. I'm drawing my slots. And I can see, of course, then I have what? N minus 3 slots left over here. I'm thinking about my ternary string of length n. I guess I didn't say of length n. I should have added that here, of length n. I think it's probably clear from the context. A sub n is, the number of ternary strings of length n. Anyway, so if I've filled the first 3 slots with zeros, then I have n minus 3 slots here. But you see, it doesn't matter what you put in those slots. Everybody in this case is supposed to be counted as part of this total that we're calculating. And so what we're going to be doing in a minute over here is figuring out how many strings are in that case. And does anybody want to tell me now what it is? Maybe we already know. Fernando?
Is it 3 raised to the n?
3 raised to the n minus 3 strings here. That's absolutely right. Yeah, and you're just getting it from the multiplication principle, right? 3 choices for each slot. 3 choices, 3 choices, 3 choices all the way along the line, and there's n minus 3 slots there. It doesn't matter what you choose, a 0, a 1, or a 2, you already have 3 consecutive zeros already built into here, okay? Now, by the way, just so we're clear, I mean, you could imagine saying, well, what if I wanted to start off my string that way? That's fine, okay, but then you also have another case that, you'd have to look at that as well, and these would be non-overlapping cases, and I would want to count both of them. And there's no need to break this into these 2 cases because they both kind of merge into this one case that covers all of those. So it's not that this would be wrong to imagine like starting off with 4 spaces filled in, but it's going to give you a more complicated recurrence relation than what you need. So I would, again, with practice, you'll get a little better at figuring out like exactly how to make your cases. Here, I don't need to say anything else about what's after that last 0. It could be another 0, but it also could be a 1 or it could be a 2, and that's fine. Makes no difference. Okay, so that's one case. Let's think about some other cases. So any other case I write down should not start with 3 zeros in a row. Does somebody want to give me one? 0, 0, and 1. Okay, so we could start off like that. That's a great idea. So now in this case, we don't have three consecutive zeros yet, and in fact, we haven't even started getting three consecutive zeros. So if there are going to be any ternary strings in this case, they would have to be completely sitting within these n minus 3 slots. And so by definition, that's a sub n minus 3 strings in this case. Right? You have no choice. You're fixing these three and saying, I have no choice there. So then what's going on over here? Well, anything could happen over here. But how many of these strings have three consecutive zeros? By definition, it would be that many. Yeah,
How do I know there's three consecutive zeros in there? Like, what if every other term was like?
there might not be, there might not be, but how many of these strings would have three consecutive zeros? It's this many, if I was counting them.
Like that many could have three consecutive? Or
That many will have three consecutive zeros. So if this, let's say n is 10. All right, then great. So then this is 7 slots. How many ternary strings of length 7 have three consecutive zeros? By definition, that's what we're calling A7. So we're just adding that in there. It's sort of like you're taking you're just imagining that your string has this many slots. You're saying how many of them have three consecutive zeros? That's by definition A sub n minus 3. And you're just stacking 0, 0, 1 in the front of it, which doesn't change the fact that it already has three consecutive zeros, that your string already has three consecutive zeros over here.
Oh, okay. Thank
Yeah.
you.
Good question. Everybody else okay? Is that a hand? Yes. And do we have to multiply that by 2 because there's a 0, 0, 2? You can do one of two things. You can either come back up here and write 1 or 2 here, and then put a 2 there, or you can make another case, which is actually what I was going to do. So I can make another case, guys, which I think I will, just to really elaborate this. We could start off with 0, 0, and 2. And then again, I have n minus 3 slots here. And again, I will get a sub n minus 3 strings in that case. Okay, I need somebody to give me another case. One more time, Kasha?
0, 1.
0 and then a 1 right away. All right, excellent. And so that leaves me with n minus 2 slots. And again, see, the thing you're noticing, I hope, is that the last number I'm writing down, except for the first case, the last number I'm writing down is either a 1 or a 2. And that's on purpose, because what I want to do is I don't want part of my three consecutive zeros to be kind of hanging out here in the end of this first part. So if I put a 1 here or a 2 here, then if there's three consecutive zeros, it must be completely within these n minus 2 slots. And how many of these would we say that there are?
A sub n minus 2.
Right, a sub n minus 2 strings here. The other thing, as I go along, I'm just double checking, I'm not overlapping any cases. There's no string that could be in two different cases. Okay, what would be the next one?
0, 0, 2.
0, 2. I think I heard 0, 2. That sounds good to me. So I do 0, 2. This is again n minus 2 slots here, and a sub n minus 2 here as well. So nothing terribly different there. And then what else do I need? Starting with a 1. Excellent. So we start with a 1. And then how many of those are there going to be? A sub n minus 1 strings in that case. Very good. And are we done? No. We also might start with a 2. Okay, great. And so that would be a sub n minus 1 as well. No string could ever be in more than one case. And all of the ternary strings that we want to count would be contributing exactly once to one of these cases. So now my formula for a sub n, if you don't mind, I'm actually going to write the terms in the reverse order of how I did them here. So I'll start with 2 copies of a n minus 1, and then 2 copies of a n minus 2, and then 2 copies of a n minus 3, and then I'll end with 3 to the power of n minus 3. So there is the whole story on that. Fernando.
Is there a way to be able to like find the minimum number of cases that you need for this? 'Cause I guess because you can have more than these cases that we've listed here, right? But it just wouldn't be like helpful.
Yeah, to do any better. Again, if you combine like cases 2 and 3 into 1, or 5 into 1, 6 and 7 into 1, that would reduce the number of cases. I don't think you can get any better than that, actually. If I did want to really, from a practical perspective, use this, I would need some initial conditions. So I would probably want to start off with, in fact, the number of initial conditions that you would want to write down should always match how many of the previous terms are required to actually evaluate this. So in this case, I would want to write down A1, A2, and A3. Can anybody tell me what are those three numbers? Okay, this is not very difficult, right? 3 consecutive zeros, you can't get 3 consecutive zeros until you at least have a string of length 3. And if your string has length 3, there will be one way to get 3 consecutive zeros, which is just 0, 0, 0. So those are your initial conditions. So if I now asked you to find, I don't know, maybe how many ternary strings of length 6 have 3 consecutive zeros, we could just build up to that. So actually, I should say something here. If I wanted to know A6, I could either build up to it or I could break down from it. I'm going to recommend building up to it. Because you could start with A6 and then say, oh, I'm going to write it in terms of A5, A4, and A3. But then you have to take each of those and write them in terms of something smaller, and it's a bunch of algebra. Okay, it's not that it's wrong, but it's just messy. This is just very easy to just work forwards from A4 down to A5 down to A6. So for example, A4 is just 2 times each of the previous things added together, which I guess would be 2 plus 3. So that should come out to 5. If I did that right. So I'm plugging in n equals 4 right here. I just get 3 here and I just get 2 here. 2 plus 3 is 5.
So the 5 represents the total number of strings that like satisfy the.
Yeah, that have 3 consecutive zeros in them. So I wonder if I can write them all down here.
So like,
Something like that. Actually, 5 doesn't look right to me.
It's only 4 digits.
Oh, this is only 4 digits. I was like, what's going on here? I'm only supposed to have four numbers here. Okay, so like I would have 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 2, 1, 0, 0, 0, and 2, 0, 0, 0. Those are the 5 strings that have 3 consecutive zeros in them. I was getting worried there for a minute. It's like, wait a minute. Yeah.
Start with A zero.
Well, I don't like to do that because then how do you define that? You have to have some convention. Natural convention would be that A0 is just equal to 0. Because there wouldn't be any strings of length 0, but it's a physical object that doesn't make sense. So it's kind of like starting with 0 factorial. You have to sort of assume that that equals 1. And those kind of assumptions can be a problem if they don't reflect the physical reality of the problem. So I prefer not to do that. Yeah.
is the idea that before, like if you had asked us the same question, but for a specific n like 4, we could have answered it by like just figuring it out, but now it's like general for any.
Yeah, like if I ask you to do the A5, which is what I was about to write down, it's gonna be hard. Let's see, what would A5 be? It would be 2 times each of the 3 previous ones, so that's 5 plus 1 plus 0 is 6. You gotta double that, which is 12, plus 3 squared, which is 9, that's 21. That's why I was getting nervous. I was getting all the way, there were gonna be 21 of those. And then what's A6, just for curiosity, I have to take 2 times each of the 3 previous numbers. So if I add these up, this is 27 for these 3, and then double that, 54 plus 3 cubed. That's 54 plus 27, which is 81, I think. Doing a lot of mental math here. So it goes up quickly. And you can see that that would not be easy to directly do. Like that's already not something you want to do by hand. Okay, so you can go dot, dot, dot on that. But that's kind of how I would do it. Does this make sense how I'm evaluating these? Everybody could kind of do that. Okay, the numbers aren't too bad there. Let's do one more warm up and then we'll move on to skill number 2 over there. So I haven't talked about, so obviously I could do this forever, but what would be so much nicer would be to have a generic formula for A sub n that I just plug n into, right? We'd much prefer that than having to sort of fumble through this long list. If I wanted to get up to A20, we'd be here all day just to build it up like this, right? So it'd be nice if there was just a plug-in formula that I could directly go to. But let's try, so these are the initial conditions. I'll go ahead and label them as such, and then let's try another example. So I kind of like this one as well. I'll do this as another example. Find a recurrence relation. By the way, before I forget, I think there's some problems on the homework that you're working on where they have tiles of length n. They have like red and green tiles or something. Now keep in mind, that's really just bit strings of zeros and ones. It's just with colors instead of numbers. So it more or less is this same kind of problem. So you'll see that in the homework. Here's one that I'd like to try with you guys. Find a recurrence relation for the number. And this time I'm going to use S sub n, the number of ways to climb n stairs if you can climb 1, 2, or 3 at a time. I think I had a problem, last time I taught this class last year, I think I had a problem on my exam, which was the same problem, except that you could either climb or crawl. And then, but you can only crawl, like you can't crawl 3, you can crawl up to 3 stairs. So there was like several constraints that made it kind of an interesting problem. For now, let's just do this one. It's kind of an easier warm up. So you're gonna go up this staircase, right? And you're going up 1, 2, or 3 steps at a time, essentially. Okay, so you can do it however you want. And so let's try to solve that. So I guess, again, I'd like to think about cases. And over here, I was just thinking about how does the ternary string start? Over here, what I'd recommend you do is you sort of imagine you're down here at the bottom of the staircase. And what are the different ways that you could start, right? Well, you have 3 things you can do. You can go up 1 stair, or you can go up 2, or you can go up 3. And each of those would be a different pattern of climbing the staircase. So we can make 3 cases. So we have 3 cases. First case is start with a 1 step. You just step up 1. So I'm just gonna put myself right here onto that stair, and then after that, I have a staircase of length n minus 1 left over, right? And how many ways would there be to complete the climbing of this n step staircase if I started with the 1 step? Great, S sub n minus 1. I'll just say S sub n minus 1 ways to finish the climb.
Do you mind explaining that, Professor? I was confused on the A sub n too. Like what is the S sub n minus 1?
This is just denoting the number, so the n is the size of the number of stairs I'm taking. So if I've walked up 1 step, then the remaining staircase has n minus 1 stairs on it. And how many ways are there to climb the rest of that staircase? I don't, without writing out what the cases are, I just know that my name for that number would be Sn minus 1.
So it
Makes
could be
sense.
1, 2, or 3 steps per, like the next step.
Yeah, I have no idea how we're handling what's in here. We don't even know what this number is yet, right? But it's in some kind of a relationship with Sn, right? The Sn minus 1 is related to the Sn somehow. Am I making any sense here? Okay, what would be a second case? Start with 2 steps, with this 2 step. So start with a 2 step. So funny, it reminds me of my dad. He climbs stairs 2 at a time, and then he complains that his knees hurt. And he had to, it was so funny. Then he scheduled this knee replacement, which he just did last week. And even as recently as like the last time I saw him, he was still doing this, like going up 2 stairs and I'm like, Dad, come on, just take 1 step at a time. You'll save your knees. Yeah, so this will be S sub n minus 2 ways to finish the staircase. I have not seen him try to do 3 stairs at one time, thank goodness. That would be even more impressive, but we could start with a 3 step. Okay, so start with a 3-step. And in this case, there would be S sub n minus 3 ways to finish. And so my formula then, again, I just add up these cases. Sn is equal to Sn minus 1 plus Sn minus 2 plus Sn minus 3. And I guess I should also add, how many initial conditions would we want to have here? 3 of them, right? So initial conditions. And again, I'd rather not think about a staircase with 0 stairs on it. So for my initial conditions, let's focus on something that is realistic. Let's say that we have either 1, 2, or 3 steps. So how many ways are there to walk up 1 step? Just one way, right? You just have to take the 1 step. How many ways are there to go up 2 steps? 2 ways, because you can either take 2 single steps or you can do 1 double step right away. What about a 3-step? How many ways are there going to be to do that? 4. So I could take all 3 in 1 jump, right? Or I could do a 2 followed by a 1, or a 1 followed by a 2, or 3 individual steps. Okay, that sounds like 4 ways. So you just have to think through, the base cases on this. To get those written down, and then from there I could solve for a S4, S5, S6, S whatever, right? I could do any of them. Yeah, Nikolai?
I understand.
Yeah.
Six.
Well, and the same thing here. I could keep going. I could figure out, well, I wonder what S4 is, what S5 is. You can obviously manufacture additional initial values if you wanted to. And so if you were solving a problem and you weren't sure how many initial conditions you should probably have,
Yeah.
you could always just cover yourself by saying, I'm just gonna do a whole bunch. But the minimum number that you need to do is sort of however many previous terms the recurrence relation relies on. Actually, there's a word for this I'm about to write down, which is the order of the recurrence relation. So I'll put that in the notes in a second, but yeah, that's kind of what dictates that sort of thing. Okay, is everybody good on that? Any questions so far on that? Okay, so that's kind of the introduction section of recurrence relations, and that's kind of how you set up these things, but then the value of it isn't very good unless we know how to solve them as well. So I want to talk a little bit about number 2, and this is the part that is going to reminds me at least of differential equations because I teach it all the time. It is a little bit cookbook, which isn't usually my favorite thing to teach. I'm not saying I don't like to teach this. I'm just saying it's because it's kind of just, all right, here's the rubric for how to work it out. So just bear with me if it feels a little bit slow, it won't last that long. We are going to be skipping ahead though to 7.4. So far, everything has just been kind of the first part of chapter 7. I'm jumping ahead. I'm essentially going to skip over the stuff on generating functions and come back to that. So I'm going to skip up to this section here, which is about linear homogeneous recurrence relations. This is the idea. Linear homogeneous recurrence relations. So let me just put down the definition here. This will all feed into helping us solve these recurrence relations. So a linear, guess I'm going to write it out again, guys. A linear recurrence relation. So I'll leave out the word homogeneous for the moment. A linear recurrence relation of order K, a linear recurrence relation of order K has the form so I have to get the form down so we all know what we're looking at. Now it's going to be H sub n. I'll use H for this just to be consistent with the book. A1 times H n minus 1 plus A2 times H n minus 2. and dot, 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 up to, let's say, A sub k times H sub n minus k, and then plus some term on the end of that, which is going to be denoted as B sub n. And this is where the A sub i's and the Bn, they don't have to, but they may depend on n. You might see the n in them or you might not, is what I'm saying. They could be numbers. The a's could be like they are here, right? You see 2, 2, 2, like you can have just scalar coefficients, but they could also be functions of n, like on this example, you see the 3 to the n minus 3. There's an n up there. That would be, this is kind of the b sub n portion, right? So you have that there. A quick little remark here about this definition. So the order is k. Noticed, we need k initial values. We need k initial conditions or values here. Let's just say H1, H2, and dot, dot, dot up to HK. Again, if H0 makes sense, I don't mind that being an initial value as well. But typically, you might use the first k numbers starting with H1 to solve a recurrence relation, right, of order k. Right. Okay. So we talked about the initial conditions there. And based on this form, that's going to help us to actually solve these things. One more definition here. I've got the word homogeneous up there at the top of the board. Let me just add what that's referring to. So if B sub n is equal to 0, if there is no term that is not hitched to a previous term of the sequence, if B sub n is equal to 0, then the recurrence relation is homogeneous. Sorry, this is for all n. If B sub n is equal to 0 for all n, so B1, B2, B3, they're all equal to 0. The relation is homogeneous. The recurrence relation is homogeneous in that case. That just means it's not there. You just don't have that. Then it's homogeneous.
So that one's not homogeneous.
This one's not, and this one is. I'm gonna write down some examples. Yeah, I'll write down some examples of that for sure. Yeah, and also one other definition, and then and then I promise I will go to the examples. If all of these A's, the coefficients here, if they're all just constants, then we're gonna call it a constant coefficient recurrence relation. See, this is just like differential equations. It literally is like my same lecture. I just have to change the word differential equation to recurrence relation, and my lecture carries over. Maybe next year I'll do that, save myself some time. Right, so if the A sub i's are constants for all I, if all of those are constants, then the recurrence relation is constant coefficient. Yeah, so that's a constant coefficient homogeneous recurrence relation would have just constants in front of these h's and would not have a b term, for example. Pretty easy. Let's just write down a couple of examples. We've already got several on the board here already. So let's just let's use the two that we've already written down to start off with. So the first one, an equals 2an minus 1 plus 2an minus 2 plus 2an minus 3 plus 3 to the power of n minus 3. Can somebody tell me the order of that? Order would be 3, right? That's how many previous terms you have to go back to. It has order 3, and is it homogeneous or not homogeneous? It's not homogeneous because there is a b sub n part, which is this power of 3 here. So I'll just say not homogeneous. It's obviously constant coefficient. I won't write all that down. The constants are just 2 in front of all of those. So that's not constant coefficient, but it has order 3. What about the one over there? So if we took Sn, which is Sn minus 1 plus Sn minus 2, sorry guys, I am going kind of quickly through this just because it's just basic definitions here. So the staircase example, it still has order 3, right? But this one is homogeneous. So this one has order 3 and is homogeneous. Looks pretty good to me. Do another one. Well, we can't neglect our famous Fibonacci sequence. So the recurrence relation for that, Fn equals Fn minus 1 plus Fn minus 2. What would be the order of that one? 2, right? So it has order 2, very good. And is it homogeneous or not homogeneous? And it is homogeneous. Okay, so I'll just use a ditto symbol on that to save a little writing for us. And let's write down one more, just for good measure here. Write down a fourth example, which might be, let's do something with the derangements. We've certainly given some recurrence relations for derangements before. So I'll use d sub n on this one, and this one I'm going to use the quantity n minus 1 times the quantity dn minus 1 plus dn minus 2. This is an example that I did in my review session for the midterm a week and a half ago or so. And what would be the order of this one? 2, right? This has order 2. And is it homogeneous or not homogeneous? It is homogeneous because every term is if you wanted, you could multiply it out. You know, and that would be fine. Then you can kind of see more clearly that this is like A1 times H1 plus A2 times H2, and there is no B, and there is no term that is besides itself that doesn't have the D's with it. Like every single term here has a D with it. So this thing has order 2 and is homogeneous. The only thing about this one that is different is this one is not constant coefficient. So it is homogeneous, but not constant coefficient. As you can see, the coefficients there have n's in them. So yeah, so that would be another good example, I think. Okay, all this okay so far?
Just a quick question, you mean like not constant coefficient? What, right?
Yeah, I just mean, yeah, these coefficients are not just numbers. I mean, they depend on n. They're not the same for every value of n.
And then for the example number 1, the b sub n is 3 to the n minus 3.
Yeah, so this is the b sub n right here. That's a good point as well.
And what about that makes it b sub n? Because it has n, right? But
It just doesn't
the
have any of the h, it doesn't have any of the a's in it.
Gotcha.
That's the reason that we can kind of pick that one out and say, oh, that's the not homogeneous part. Yeah, exactly. Okay. Any other questions so far? Okay, let's talk about how to solve these recurrence relations. So now that we've got some definitions, by the way, guys, you know, when you study differential equations, you learn that you can't solve all of them in the world. And even specialists in differential equations can't sort of ever get to a point of knowing how to solve every one of them. The same thing is true here. If the recurrence relation is not linear, if it, you know, isn't somehow nice, that either being homogeneous or constant coefficient or something like that, we could write down a horrendous recurrence relation and have no idea how to get a closed form formula for it. So I don't want to disillusion anybody into thinking that, oh, well, we're going to be able to do every recurrence relation out there. We can always do this plugging the information we have into the next one and the next one and the next one. That's kind of a basic thing you can always do. But in terms of actually getting a closed form formula for A sub n, or H sub n, sorry, you cannot always do that, as it turns out. Let's talk about how to do it when we can do it. So how to solve let's just make it really easy, constant coefficient. So we will assume it has constant coefficient. So I'm not talking about number 4 here. Example 4 is not going to apply right now. Homogeneous recurrence relation. Can I just use RR? When I do differential equations, I just write it DE, and everybody seems to do fine. So I think you'll know what I mean by that. Well, the answer for how to do this is the same answer that you have in differential equations, which is that you guess the solution. We actually did this last week. We sort of guess what the solution's form will be, and then we tweak it up so that it has exactly the right characteristics. So step 1, this should be kind of familiar, as I said, is that we are going to quote unquote get. This is another thing I don't like about this, is we're guessing an answer. It's like, that doesn't sound like you need a PhD for that. But we're gonna try it anyway. We're gonna guess a solution of the form H sub n equals Q to the n. I think that was the same notation I used last time, where Q is to be determined. Actually, that was the approach we used to come up with the explicit form for the Fibonacci numbers. You remember the one with the radical 5 in it? The big messy thing? That's how you kind of do that. So you're going to plug that in. So step 2 then is you plug this guess into the recurrence relation. So I'm actually going to take that recurrence relation though, and I'm going to move everything to the left side. So I'll go ahead and write it down here. H sub n minus A1 Hn minus 1 minus A2 Hn minus 2 and minus, right? Subtracting everything over. A sub n H sub 0 would be the last term. I'm sorry, H sub k. The last term should be H sub k. A sub k, sorry, A sub k, H sub n minus k. Blah, 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 blah. This is homogeneous, so I don't have a B right now. The B isn't here, so I'm just looking at this part, and I'm just moving everything to the left side. Subtracting everything to the left side, that's going to leave me with equals 0. Equals 0. Okay. Yeah, so when we do that, everywhere we see Hn, we're just going to put Q to the n. And so then that will be minus A1 times Q to the n minus 1 and minus A2 times Q to the n minus 2 and dot, 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 minus AK times Q to the n minus K. This is, of course, still equal to 0. I'm really not interested in Q equal to 0, so I'm going to factor that and cancel here in a second. Okay.
So why do we go to the exponent? Because you replaced like H with Q and then the n turned into the exponent.
Whatever this subscript is what that power is. So just if we look here, like this one, Hn minus 1, so this gets re-expressed as Q to the n minus 1. Yeah. Each term is like that. Now I'm going to factor and cancel those Q's. And when I do that, so I'm going to I'll just say simplify. I'm going to try to do it down here on my board. I hope you guys can read this okay. When I simplify that, I'm gonna basically divide through by q to the n minus k, so this is just a little bit of algebra here. Q to the k minus a1 times q to the k minus 1 minus a2 times q to the k minus 2 and dot dot dot. The last one would be minus ak equals to 0. So that's just dividing out as many q's as you can from every single term. Let me know if I'm going too fast, because sometimes like this isn't all that exciting, but I also don't want people to be lost. Yeah, Christian?
I don't know that Q to the N is a good guess. Like a good form of our solution.
I have no idea. You know, somebody way smarter than me, way before I was ever born, figured out that if my recurrence relation is homogeneous with constant coefficients and linear in the form that we've written down in this box over here, that it works. Actually, you only have to discover one time that that is the secret formula for how to solve these recurrence relations, and then the rest of us get to benefit forevermore off of that advantage. You know, it's also, of course, linked with differential equations. So in differential equations, given certain forms of differential equations, we guess certain forms of solutions, and there's a little more calculus involved in that case, but it's the same kind of thing. It's like, where did this come from? Somebody just discovered it. It was just discovered at some point and it works. So we're gonna take advantage of it. Great question. Hey, question.
So I'm assuming you're gonna give us the form, right? Like the
It's
guess.
in that box right there. You have to know that. Make sure you learn it. Yeah, so definitely, if I have a constant coefficient, homogeneous recurrence relation, this is what you need to know. I don't think you need to memorize all of this, because of course you could always just derive it again. It's not so big of a deal to just plug in q to the n everywhere. In fact, that's probably what I would do. Now this, my friends, is a polynomial in Q. It's like x to the k minus something times x to the k minus 1. Do you know how many solutions there will be for Q on a polynomial of degree k?
Maybe
Exactly k of them. Exactly k of them. If I have a quadratic equation, it always has 2 roots. If I have a linear equation, it always has 1 root. If I have a cubic equation, it always has 3 roots. Now, some of you are out there thinking, wait a minute, I don't think the cubic equation crosses the x-axis 3 times. You're right, because we might have to use complex numbers for some of those roots, and those complex numbers aren't going to show up on your graph. But how many roots you have, if you allow for complex roots, there would be, and for repeats, there would be k of them, right? So this has k roots. Let's just clarify that. So this has k roots, including possible repeats and or complex numbers. Anything goes. Right, you could have any of those things. Yeah, Julie?
Is Q to the n minus k a constant, the one that we factored out?
I'm not thinking of it as a constant so much, like I'm viewing it like a variable. So like I'm viewing this as like, you know, basically this kind of an expression. And so the last one would be, you know, something like that. So it's a polynomial where I don't want to think of the x as if it was a constant. If it was a constant, then there's really no roots to the equation, right? So. Oh, yeah, you factor it out, put it in the front, and then you just note that it's not 0. That q is not 0. If q is equal to 0, this isn't very interesting. So if q is equal to 0, you don't have a very interesting, it might be correct, but it's not very interesting, and it's not going to satisfy your initial conditions, most likely. So yeah, so let's just ignore that piece of it. Okay, so we've got to find these roots. Actually, that's step 3 here. There's actually 5 steps total. Step 3 is to find the roots, which I'm gonna call Q1, Q2, and dot, 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 up to Q sub A. Again, recognizing that some of those roots could be repeats. It could have the same root multiple times, or you could have complex numbers in those roots. All of that is possible. Back up here again. So then we're finally ready to start getting the form of the solution down. Be a couple of steps here for this piece of it. Right, so step 4. The next step here, step 4, is going to be if all roots are distinct. So if we don't have any repeats, then we form the general solution. I'm ready to write down the general solution to the recurrence relation, just the way I do for differential equations as well. And it would look like this: h sub n equals c1 times q1 to the n plus c2 times q2 to the n, and dot, 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 plus on and on and on, ck times q sub k to the n. And in this notation, the c's, all of those c sub i's are constants to be determined. I'll just write TBD. Constants TBD, to be determined.
So,
How do you suppose you're going to determine them?
it's constant.
That's true. Yeah, these constants, these c's do not have any relation with the a's in the original recurrence relation. Anybody have a thought? How am I going to actually find the constants?
Use your initial.
Use the initial values. That's exactly right. So notice that there's k constants here. How many initial values will we have? That remark disappeared. If the recurrence relation had order k, it was supposed to be k initial values. So you would have exactly enough initial values to solve for those constants. Okay, so that's basically the story on that case. But also with step 4, there's another possibility, which is that you could have a root. Let's just say that if a root, I'll call it q sub I, one of my roots, is repeated. Let's say it gets repeated s sub I times. Then, okay, so here it gets a little bit more complicated to write down. You're going to put together the part of the solution that goes with q. See, each of these roots kind of contributes one part of the solution here. So the first part is for q1, the second part was from the root q2, and each part up here in the first case, each part was just one term all by itself, right? So you have k individual pieces to the general solution. Here, we have to actually make the part of the solution that corresponds to q sub I into a whole big expression, okay, that seems a little more complicated. So then we construct, I have to write a couple of notes here, guys. The part of the general solution corresponding, big words. We construct the part of the general solution corresponding to q sub I. So like, what does that piece of the big general solution look like? This would just be one piece of a whole bunch of terms, right? In the h sub n formula. But what you do is you do it like, I'm using the book's notation. You emphasize that you're going to do the I piece corresponding to the q sub I root. And this is written with a capital H sub n. And what this is, here's what you do. You just start off C1 times qi to the n. Now, guys, if I stop right there, then I'm really just looking at like one of the terms that we had if all the roots were distinct. It's because this qi is a repeated root that the part of the h sub n expression that corresponds to that root actually has multiple pieces to it that I have to add together right now. The next term is C2 times n times qi to the n. And then the next term is C3 times n squared times q sub I to the n. And it goes on like this plus dot, dot, dot. The last one, so there could be several of these. The last one would be C sub Si. So notice how many terms I have. I have S sub I terms, which is exactly sort of the weight of that root. It's like how many times that root was repeated. C sub Si times n raised to the power of Si minus 1 times Qi to the n. Whew. Yeah, take a deep breath. I know Christian's gonna ask me like, how did you come up with that? You know, it's the same thing when you write. I didn't mean to give you a hard time. He's gonna give me a hard time again. When you learn how to solve differential equations, you have to kind of do something like this as well. There's a so-called auxiliary equation that has roots to it. If those roots are repeated, then you have to stack. You have to make a bunch of terms where you start stacking the variable to higher and higher powers on each term. It's the same here, right? The n is the variable now, and the n is getting stacked. Each term has one more n stacked in front of that piece of the solution here. So this is all just cookbook, guys. This is what I was saying earlier. This is not like any super creative, high-powered thing. It's just there's a fair bit to kind of like try to digest on this. But it's not something that, see, technically I don't have to prove it. Actually, this is stated in the book, I think, as a theorem or a result of something like that. But in my view, the proof of the theorem is in the when you apply it to a problem and it works on that problem, right? You find out that, oh, okay, if I use this, it actually does solve the recurrence relation. Yeah, so this is theorem 7.4.2 in the book. We want to give a reference on that. Okay, and so, yeah.
So this is, let's say, like 3 separate roots. And this is only, and let's say 2 of the roots are only once.
Yeah,
Let's say our third root repeats 5 times.
yes,
We're only gonna use this on that root that repeats.
correct. This is only for those roots that are repeating. So if I have roots that just show up once, I'll just make one term for those roots. And then when the roots start repeating, then we create this whole big colossal expression for that. Yeah, exactly. So, so what is the general solution then here? I want to get this down and then try an example because the example will make it seem a little less scary. But the general solution would then be h sub n is equal to the summation of all of these capital H sub n super i's where we sum over the I values. So you just add them all up. And what Christian is saying, I think, is that, well, if some of these roots are not repeated, then the big H is really just one of these individual terms. So in other words, what I'm saying is you can use this even if the root isn't repeating. Let's suppose S sub I is 1. If S sub I is 1, if the root doesn't really repeat, it's just there one time, then when I do this expression, I'll only get that term. Because it'll stop. If S sub I is 1, then you're already done, right? This is already n to the 0, which is already the same as what you had right here. So you can actually use this thing for each of the roots, whether it's repeating or not, and it'll work just fine. Okay, and then finally, step 5 is to use the initial values to find C1, C2, and dot, 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 up to C sub K. All the constants, basically just all of the constants, whatever they are. Okay, so let's try an example. How about see if we can make sure that this is all clear. Let's do an example. So for a quick example of this, let's take this one. Let's solve h sub n equals 3 h sub n minus 2 minus 2 h sub n minus 3 together with initial values h0 equals 1, h1 equals 0, and h2 equals 0. So we'll just kind of take an example like that. Notice I'm giving you 3 initial values. That's because this is a recurrence relation of order 3. Okay? So, solution. We can go, like, we don't really need to write down step 1. They're always the same. Just write that down. I guess I could write it down. Just so we're being very thorough, that's step 1. Okay. And then we plug that into the recurrence relation. We plug this guess into the recurrence relation. I wouldn't try to memorize all of this. It's not so helpful. I would just go ahead and just plug it in. So on the left side, I have Qn. On the right side, I have 3Qn minus 2 minus 2 times Qn minus 3. I would just do it like that. And then I'm just going to cancel as many q's as I can, and I'll have q cubed on the left. On the right, I'll have 3q minus 2. So I'm canceling as many q's as I can, which would be n minus 3 of them. So from every factor, I've canceled n minus 3 q's. That reduces it. It should be a cubic equation, because this is an order 3 recurrence relation. And I can just move everything to the left side, which I would recommend. So we're going to get something looking like so. Q cubed minus 3q plus 2 equals 0. And I guess we have to factor that. So you could look for rational roots, and you have some pretty good success with that. If you just plug in q equals 1, it works. So you could take that root and then sort of divide it into this cubic polynomial and leave yourself with a little quadratic equation to solve. I'm not going to bother with all the algebra of that. I'm just going to tell you basically what this is going to factor down to and let you guys check it. It's going to be q minus 1 quantity squared times q plus 2 equals 0. So that's just factoring, which we can easily check, of course, if we needed to. But the point being that the values of q are 1, 1, and -2. Be sure to write down repeats. If there's a repeat, write it down as many times as it repeats, just to kind of keep it clear for yourself. Okay, so now let's figure out these big H's. There are 2 of them, right? Even though there's 3 roots, there are only 2 big H's, because there's one that corresponds to the root 1, and there's one that corresponds to the root -2. So let's write this as h sub n, and I'll write this as super 1. And what does that look like? So if the first root is repeated 2 times, so s sub 1 would be 2, then the part of the solution that corresponds to that, it should look like the following. C1 times 1 to the n plus C2 times n times 1 to the n. Guys, try not to get lost in all this notation over here. The only thing you have to remember is that the number of terms that you write down here should just match the number of repeats. So if the root shows up twice, you should do 2 terms and then you just stop. So cookbook as as it gets, right? And then the other H, which I'm going to denote as H super sub n super -2. Of course, I need to use a different name for the constant, so I'll use C3 for this one. But again, it's just, this one only has 1 term, so it's just C3 times -2 to the n. And now I'm just going to add those together, right? So H sub n, this is the big punchline, H sub n will be C1 plus C2 times n plus C3 times -2 raised to the n. That would be that's what we're calling the general solution. So it's just one of these, so that root is not repeated, so it's like that term or that term. It's just got a constant and then the root to the power. Yeah, don't get no. These constants are not lining up exactly with this. So on our example here, we don't even have this much of the solution, right? We only have the first 2 terms, and then I'm just adding this 3rd term onto the. Yeah. Good point. Okay, so I've made it how far into my 5 steps? Everything except the last part, right? I just have to solve for the constants. Okay, so let's take do we have initial conditions? We do.
Yeah.
Oh, good. I love it when it works out. Question?
Yes.
Everybody good out there? I hear some chitter chattering, so I'm wondering.
Alright, I do have a quick question for, I got every step, but I'm not connecting the Q2 to the Q3. How do we get to there?
Excuse me?
The Q, on the left side.
Here?
That-
Oh, this, you just divide through by q to the n minus 3 everywhere.
Oh,
That's it, on all 3 terms. Was that your question, Nikolai? No. What was your question?
Well, it had more to do with. Might just wait until. I'm confused why it's each cube is raised. Did we get there from step 2, or is that just?
Well, it's kind of, the original idea behind this was that all of the terms that we're trying to write down have this form q to the n. So if we start finding q values that are roots of our equation that was in step 2, which unfortunately is erased now, but in that equation, when we find those roots, the natural idea would be to try to make them fit in with this program, which was, we were assuming that the roots were going to look, or that the terms of the solution were going to look like that. Yeah. Teresa?
For our initial conditions, does it relate to our repeated roots? Like we had like our H1 or H2 are both equal to 0. and
That's
then-
just a total coincidence.
Okay.
Yeah, it just happens to be here that 2 of the roots are repeated, or 2 of the initial values are repeated, but that could be anything. It doesn't necessarily have to line up like that. Good. Okay, let's just solve for the constants. If I plug in, so H0, on the one hand, it's supposed to equal 1. That was given. But if I put in 0 for n everywhere here, I'm just gonna get C1 plus C3, I believe. I'll just put in n equals 0. If I put in n equals 1, I'm also supposed to get 0. So let's just do that as well. If I plug in 1 everywhere I see an n, I'll have C1 plus C2 minus 2C3. Am I okay? I'm just plugging in n equals 1 into this. So I just get C1 plus C2 minus 2C3. I have to do the next one, right? H2. H2 was also given as 0. So I put in 2 everywhere C and N. I'm just getting C1 plus 2C2 plus 4C3. And there you go. You have a system of 3 equations and 3 unknowns. And you're going to solve it. I'm not going to do it right now. Just going to tell you what it is, because this is just a easy thing from another class somewhere. Hopefully anyway. So it turns out that C1 turns out to be 8/9. C2 turns out to be -2/3. And C3 turns out to be 1/9. So you can check that. I don't want to do it right this moment because it's just 3 equations and 3 unknowns. Put it into an augmented matrix, make my 250B students proud. You can be downstairs outside my office doing this, and they're gonna be like, oh, wow, the stuff I'm learning in 250B is actually useful for these math majors. Everybody will be happy. Yes, demonstrate outside my office for all my 250B students that even now, that's stuff, because they hate this. They absolutely hate having to like solve these augmented matrices.
Wait till they find out they can.
So now I'm gonna put the numbers in here. Here's my general solution right here. There's my general solution. Because this problem had no physical nature behind it, it doesn't necessarily bother me that there are fractions in the answer. But of course, if H sub n was supposed to be counting the number of ternary strings with some conditions, those fractions would make me nervous. There shouldn't be fractional numbers of ways to do things. So just kind of keep that in mind. It's a little nerve-wracking if it's a physical problem that's supposed to be whole number values. Sometimes you can have fractions that somehow simplify to whole numbers when you start plugging values in for n. But here that may not be the case, and it doesn't really have to be the case. Yeah. I tell you what, guys, we're basically out of time. I am going to, sometime when I have time, hopefully in the next few hours, I am probably going to record a little video for you to watch, because I somehow got behind today. I want to talk about how do you solve the non-homogeneous case. But what if there is a BN term there? It's still cookbook. Actually, the first step of the non-homogeneous case is to just solve the homogeneous one. Does that sound like differential equations? Same thing, right? So I'd like to go over that and then maybe do an example. So I might record a little video and send it out by the end of the evening. See if you can watch it. That way, because I do want to try to get done with this chapter sooner than later, to stay on schedule. As a compromise for that, I'll let you go a couple minutes early because I don't want to try to start talking about it now. Are there any questions here though about how this works? Everybody good? You have to practice it a little bit. This stuff is kind of notationally thick, and it's not that hard. It really isn't that bad. All right, I will see you guys around.